In this video session then I'll talk about the averaging options here, which applies to both results for a given wind condition and for the production estimates. And to do this then we would actually need to know about the model, and there's not time enough for that, but I can show you here how to read more. You can go to www.wasp.dk and then click on Fuga page, and here at the bottom of this page here's a link to a report which you can read, and it should be explained in there. But for now then I'll just talk a little bit very fast, explain what it's about. And first we will remind you that we have this model for the wake effects, that first you know that at the upwind conditions then it's the free wind speed, then there's some wake sheltering here at the second turbine, so it's running at a lower thrust, and it will also depend on how directly the wake will impact on the rotor plane here. And then when you know the thrust of these two turbines, then you know the wakes of both turbines here at this one, and you can combine them and then look up what is the wake effect here, and so on until you know the conditions for all the turbines in the wind farm. Then during the course then we developed this method here that instead of just looking up the conditions here at the center of the hub of the turbine, and then look up at the power curve, then we said if there's a sort of a half wake conditions, then it would maybe be better to consider kind of how much is the effect here. So we are looking up the wind speed at 7 points here and do some averaging, and then use these to calculate sort of an effective turbulence or effective wind speed, and then look up at the power curve. I should say that actually now when you think about it, then we are not so happy about this. Maybe that is too simple interpretation. So be a little bit careful if you use this option, or maybe write to us for further research on this. Then there was in the model, then the wind's direction is always completely steady and exactly the same everywhere in the flow domain, and but in reality there will be some movements of the wake because the wind is turbulent, so it's moved from side to side. So you could sort of expand the model to do like this, that you have this curve here, and then see if what is the conditions here, and then simulate how much impact it is. And we did that first we used the model of Jagerman and then tracked particles in it here, and then we fitted a simpler stochastic model, and then we could use that to simulate the displacement here. So we can just go in one jump here and say what is the displacement here, and then to the next, and what is the jump here. So then we had a very fast stochastic model catching this displacement due to wake-meandering, and that would be a stochastic simulation. So the result would be a little bit different every time, but then the interesting thing would there be sort of a bias due to this, because then the problem is here, if you have this turbine and then what are the conditions on this, and they will be a little bit random, and then maybe there's an effect of this. Then if we look at these conditions here, which we need to calculate the annual energy production, then we could start with doing some modeling for specific wind speeds or wind directions, and then we could do some averaging here by saying we want to average over a little sector, saying maybe plus minus 5 degrees or something like this. That was actually the first we did, and you could say that that would be sort of a poor man's meander model. And we could also do it with Gaussian shapes. And to do that efficiently, then actually calculate all the or solutions for all the directions, and then we use a filter in, and then do it actually in Fourier space. That's faster. And then there are also two additional corrections here, which I'll go to another presentation to see something about this. The idea is that this sample here, this is 2 hours of measurements of wind direction, and as you can see for the green line here, then it's fluctuating, and mostly we are talking about 10-minute statistics, and this is what we get when we ask for data, for scatter data from a wind farm. This is usually what we get. But the point is that the wind is not steady. So what to do about this? Then we could say, what is, for instance, what is the trend of the wind direction in that? And of course it's not always the same, but it has a sort of a statistical distribution. And then Søren Ott, who did all the development of Fuga, he also investigated some data from Hornsrev here, and then he could see that they all fitted a quite simple distribution, these differences in wind direction during 2 10-minute periods. And you could model this by an exponential or double exponential distribution, so it would decay to either side here. And the spreading here, that would depend on wind speeds. And that is also what is expected, for instance, from smoke dispersion experiments, that the lower the wind speeds, the more variable the wind direction is. But that is, or then he used the data here to fit the parameters for this model, and he did this for different stabilities here. So inside Fuga, there's a little model here that you use exponential distribution for the wind direction, or jumps in wind directions, and it depends on friction velocity, which is proportional to wind speeds in some way. And then we use different constants in this model for different stabilities. But this is just a probability distribution of the jumps in wind direction. It does not, to see what is the effect of this, then you need to do some calculations, and then you can see that you get some filtering here, which is depending on the incomplete gamma function, and the same parameter as was used here, which we realized that depended on wind speed, and also on the on x here, which actually I think that's the jump in wind direction, again just written as x. So you get this this distribution like you see here. Then we could use this as a filter for the effect of the wind direction not being steady. But then if you think further, then often in these wind farms the wind direction is measured at a mast, and that mast could be representing the whole wind farm. So for some wind turbines it would be many kilometers away, and if you're just measuring over 10 minutes, then the wind direction is not exactly the same at these conditions here. So then there's a new effect here, which you could call a spatial D correlation of wind direction. So if you have a mast here, a reference mast here, and you consider one of the turbines, then you would need a slightly different filter. It's a sort of a variation of this effect of wind direction, but now also considering that there's some sort of statistical decorrelation here. So that was a long explanation of this filter which we use for effects of changing winds, and also that we really don't really know what the wind direction is, because it's measured not exactly where we need it, but maybe several kilometers away. So and also, if you want to know more about this, then you should read the report, which you can get from the homepage. Now inside Fuga, here is some options here. So I could say, if I want to do some simple averaging, now it's doing some calculations here, and then that would be sort of the half width of my filter here. So I'm using a top hat filter with over a sector of 8 degrees, and I could do similar Gaussian filter, and I could see what is the effect of rotor-averaging here. And also you could do this, apply this wind direction trends filter here, and you could if you click here on meandering, then it would do a simulation while it's calculating this annual production. Then you'll get a result which includes this variation due to meandering, and then these results would be a little bit different each time. So you could repeat the simulation several times and then get the average here. About this spatial decorrelation, then maybe I can show here, and I think I'll just take the simple case here. Now we are considering the wind trend, and let's just consider this turbine here. That would be the M1, and we have a reference site which is now this turbine over here, where I have my mouse pointer. If I move it closer, for instance, to this M2, then the results down here, they will change because we know the wind better. Oh, I forgot. That's when I click this spatial decorrelation. So now I click spatial decorrelation, and the result should not be very much different, because now the reference site is close to 1. Let's go back to this here, and the distance is now, it's about 10 kilometers. Yeah, and now you can see that it's smoother here. So Søren, he developed all these tools here when he was doing some comparisons with real data, and actually it's much more difficult than people really think when you consider how are the data measured. It's only 10 minutes periods, and the wind is not steady. But then I would say that if you're only interested in the production estimates here for the whole wind farms, then all these filterings doesn't matter so much. It's mainly when you're considering specific cases here and you want to compare your model with some data, then they are important. But for production, then they're not so important.